Hey everyone, and welcome back to Key Safety Talks. Today we're diving into a topic that's, it's absolutely fundamental to safety. It's accident causation and investigation.
Yeah.
It's really like detective work, trying to piece together why things go wrong so we can prevent them from happening again.
That's a great way to put it. And just like detectives, we've got all these different theories and tools to help us solve these cases.
Yeah, and some of those tools are surprisingly old. We're going all the way back to the 1930s with Heinrich's domino theory, but it's still incredibly relevant today.
Absolutely. It's a great place to start because it really gives you that visual of a chain reaction. Think of a line of dominoes, you tip one over and they all fall in sequence. Heinrich believed accidents work the same way.
Okay, so walk us through those dominoes. What are the steps in this chain reaction of accidents?
Well, the first domino is all about that social environment and inherited behaviors. Things like cultural norms around safety, people's attitudes towards risk, even personality traits that might make someone more prone to taking risks.
So it's like the foundation, the context where everything else happens. What tips over that first domino?
That's where the fault of the person comes in. Think carelessness, recklessness, rushing, fatigue, anything that compromises a person's judgment or ability to work safely.
Okay, so 2 dominoes down, what's next?
Now we get to the actions themselves, unsafe acts and conditions. Unsafe acts are things like not wearing your safety glasses when you should be, operating machinery you're not trained for, or taking shortcuts. Unsafe conditions, on the other hand, are hazards in the environment, like faulty equipment, poor lighting, or a slippery floor.
So these unsafe actions and conditions, these are the direct triggers for the accident.
Exactly. That's the 4th domino falling, the accident itself, which leads to the 5th and final domino, the injury or damage that happens.
So it's this domino effect. One mistake leads to another and boom, there's an accident. But the real question is, how do we stop this chain reaction?
That's the beauty of the domino theory. It tells us you don't have to wait for all 5 dominoes to fall. If you remove A and Y domino in the chain, you prevent the accident.
No, that's a powerful idea. But how do we actually remove those dominoes?
Well, Heinrich gave us a roadmap with his 3 E's of accident prevention: engineering, education, and enforcement.
Let's break those down. What does engineering have to do with preventing accidents?
Engineering is all about designing safety into the system right from the start. Think guardrails on machinery, ergonomic workstations, or safety features built into tools. It's eliminating the hazard itself whenever possible.
So it's like building a world where it's harder to make mistakes.
Exactly. A good example is the development of seatbelts in cars. Before seatbelts, people were ejected from vehicles even in minor crashes and suffered severe injuries. By engineering this simple safety feature into cars, we've prevented countless fatalities.
That's a perfect illustration. What about education? How does that fit into preventing accidents?
Education is all about empowering people with the knowledge and skills they need to work safely. Think training programs, clear instructions, safety manuals, even those signs we sometimes ignore. It's about making sure everyone understands the risks and how to mitigate them.
So it's about closing that knowledge gap that can lead to mistakes. Makes sense. And lastly, we have enforcement. What does that entail?
Enforcement is all about making sure those safety rules and procedures are actually being followed. It could be anything from regular safety inspections to disciplinary actions for repeated violations. The goal is to create a culture where safety is a top priority and not something people just talk about.
So it's about making sure those safety measures have teeth, that there are consequences for not taking them seriously.
Right. And it can be as simple as a supervisor reminding someone to wear their safety glasses, or as complex as a company-wide policy with regular audits and checks.
Okay, so the domino theory gives us a clear framework. Accidents happen in a sequence, and we can intervene at any stage to prevent them. But doesn't really get into the why behind human behavior, does it?
You're right. That's where the human factors theory comes in. It goes deeper, exploring why we as humans make mistakes in the first place.
Okay, I'm intrigued. Everyone makes mistakes, but why do they happen? Especially when it comes to safety.
The human factors theory recognizes that we're not perfect, and our actions or inactions are often influenced by all sorts of factors. It helps us categorize those human errors into 3 main types: overload, inappropriate response, and inappropriate activities.
Okay, let's unpack those categories. What does overload look like in a real-world scenario?
Imagine you're an air traffic controller and you're juggling multiple planes coming in for landing during rush hour. The weather's bad, there's tons of noise and chatter on the radio, and you're feeling the pressure to keep everything moving smoothly. That's classic overload. You're being bombarded with information and demands way more than you can handle.
And in that situation, even a small lapse in attention could be catastrophic. It makes you realize how vulnerable we are to making errors when we're pushed beyond our limits. What about inappropriate response? What's an example of that?
Think about a construction worker who sees a crack in a scaffolding but decides to ignore it because they're in a hurry to finish the job. They might think, it's probably fine. But that's an inappropriate response to a clear hazard. They've recognized the danger, but chosen to ignore it, which increases the risk of an accident.
So sometimes it's about understanding the risk, but making a bad call in the moment. What about those inappropriate activities? What does that category cover?
This one's for situations where someone does something that's just plain wrong. Often because of a lack of knowledge or training. Like, imagine someone using a forklift to lift something way too heavy. They might not realize the danger or overestimate the machine, and that could lead to a serious accident.
Those examples really bring these concepts to life, and it highlights how understanding these different types of human errors can help us design systems that are more forgiving, that anticipate potential mistakes, and minimize accidents.
Exactly. And that leads us to another interesting theory that builds on these human factors. It's called the accident-incident theory, sometimes referred to as Peterson's model.
Okay, I'm all ears. What makes Peterson's model stand out?
It goes even deeper into the human psyche and suggests that sometimes we make a conscious or unconscious decision to err.
Wait, hold on. You're saying we sometimes choose to make mistakes, even when it comes to safety? That sounds a bit counterintuitive.
It might seem that way, but think about it. Have you ever been so focused on a task that you took a shortcut, even though you knew it might not be the safest way?
You know what? I can totally relate to that. It's like when I'm rushing to make dinner and I tell myself, I can totally handle this hot pan without oven mitts, and then bam, I burn myself.
Exactly. In those moments, all these factors, like pressure, fatigue, or even overconfidence, they can influence our decisions and lead us to make mistakes, even when we know better.
So it's like we're overriding our own internal safety alarms because of external pressures or how we're feeling.
Precisely. And Peterson's model helps us understand those decisions to err. It also highlights the role of what he called ergonomic traps.
Okay, ergonomic traps sound interesting. What are those?
Think about a poorly designed workstation that forces you into awkward positions, or a tool that doesn't fit your hand properly, or confusing instructions that lead to mistakes. These are all examples of ergonomic traps.
So it's not always entirely the person's fault. Sometimes the environment itself sets them up for failure, making those errors more likely.
Exactly. And remember the Superman syndrome we mentioned earlier, that belief that we're invincible and accidents won't happen to us. Well, that can contribute to those decisions to err as well.
It's like those action heroes who jump out of exploding buildings and walk away without a scratch. But in the real world, we're not superhuman, and that false sense of security can be dangerous.
Absolutely. Remember Chernobyl. One contributing factor was the operators' overconfidence in their ability to control the reactor, even when there were warning signs. That belief that they were invincible, combined with system flaws, led to one of the worst nuclear accidents in history.
Wow, that's a chilling example of how the decision to err, mixed with overconfidence and systemic issues, can have devastating consequences.
It's a serious reminder that understanding human factors is crucial for preventing accidents. And it brings us to an important shift in perspective. What if sometimes it's not just about the individual, but the whole system they're in?
Okay, I think I see where you're going with this. We're talking about those bigger picture issues that can set people up for failure, right?
Exactly. It's what Peterson called system failure. And it's a game changer in how we approach safety.
Welcome back to Key Safety Talks, everyone. Last time, we were exploring these really interesting theories about why accidents happen. We talked about human error, those decision-to-err moments, and even how our surroundings can make us more likely to make mistakes.
Yeah, it's all about understanding all the things that can lead to accidents. It's rarely just one thing. It's this mix of human actions, problems with the system, and how the environment plays a role.
Right. And to understand all that, we've got the modern causation model. You said it builds on Heinrich's domino theory.
Yeah.
But it takes a bigger picture approach.
Exactly. The modern causation model doesn't just look at the individual, it looks at the whole system. It identifies 7 things that can lead to accidents. It's a really good tool for analyzing and preventing them.
Okay, so remind us, what are those 7 things? I remember we talked about a few of them last time, like safety management errors and those system defects, the ones that can really set people up to fail.
Right, those are key. The full list is safety management errors, safety program defects, command errors, system defects, operating errors, the mishap itself, and the consequences.
Okay, so we talked about the first 4 last time. Let's get into those operating errors now. What exactly does that mean?
Think of them as the actions, or even inactions, taken by the worker, the things that directly lead to the accident. It's that moment where something goes wrong when someone's doing their job, even if everything else leading up to that point was fine.
Okay, so can you give us some examples? What kinds of things would fall into that category?
Imagine a worker using a tool the wrong way, like using a wrench as a hammer, or forcing a tool where it doesn't fit. Or think about someone ignoring safety procedures, like not wearing gloves when they're dealing with chemicals. It could even be as simple as not keeping their work area clean, which creates a tripping hazard.
So it's not always about people intentionally doing something wrong or being reckless. It's more about those little slip-ups, those moments when we're not paying attention or we make a bad judgment call. And that can have consequences we didn't expect.
Precisely. We all have those moments when we're distracted, tired, or just not thinking straight. Understanding operating errors helps us see those weak points and find ways to reduce them.
It's like acknowledging that we're human, we're going to make mistakes. So how do we design systems that account for that and minimize the risk?
Exactly. And that's where those 3 E's we talked about earlier come back in. Engineering, education, and enforcement. They're not just for dealing with big system problems, they're also for everyday operating errors.
Okay, can you give us some concrete examples of that? How can we use those 3 E's to address operating errors specifically?
Let's start with engineering. Imagine a tool with built-in safety features that stop it from being used the wrong way, or that shut it off automatically if there's a dangerous situation. We see this a lot with power tools now. Things like kickback protection on saws or sensors that stop a machine if you remove a guard.
So it's like building safety right into the tools themselves, making it harder to make mistakes.
Exactly.
What about education? What role does that play in preventing operating errors?
Education is about making sure people know how to do their jobs safely. And that means clear, easy to understand training on how to use tools and equipment correctly, how to follow safety procedures, and how to spot and assess hazards.
So it's not just about telling people what not to do. It's about giving them the tools and the knowledge they need to do things the right way, to make those safe choices naturally.
Exactly. And the best training involves hands-on practice and feedback. Imagine a virtual reality simulation where workers can practice operating machinery in a safe environment, and they get immediate feedback on what they're doing. That kind of immersive training can be incredibly effective.
Wow, I can see how that would be a game changer. And finally, we have enforcement. How does that fit in with operating errors?
Enforcement is about building a culture where safety rules and procedures are taken seriously. This could mean having regular safety inspections, observing work practices, and even giving positive reinforcement when people are working safely.
So it's about making sure those rules aren't just words on paper, that they're actually followed and reinforced every day, that both workers and management are accountable.
Exactly. It's about creating a workplace where safety is everyone's responsibility, not just a box to check. Think about the aviation industry. They have incredibly strict safety procedures and a strong enforcement culture. That's why flying is statistically one of the safest ways to travel.
That's a great point. Those high-risk industries really show us how important a strong safety culture is. Okay, so we've covered operating errors. What about the next part of the modern causation model, the mishap itself?
The mishap is that unexpected event when something actually goes wrong, whether it's a slip and fall, a piece of equipment malfunctioning, or a chemical spill. What's important to remember is that the mishap itself is often just the tip of the iceberg.
So it's like those dominoes we talked about. The mishap is the last domino falling. But there's a whole chain of events that led up to it.
Precisely. And that's why it's so important to investigate the mishap thoroughly. We need to understand what happened, where, and why, so we can identify those points where we could have stepped in and prevented it.
And that brings us to the last part of the modern causation model, the result of the mishap. Why is it important to look at the results separately from the mishap itself?
Looking at the result helps us understand how serious the mishap was and what impact it had. It's about considering the injuries, the damage to equipment or property, and the environmental effects. The whole picture of what happened.
So it's about learning from what happened, not just what caused the accident, but also the full extent of the damage. so we can make better decisions in the future.
Exactly. Imagine two situations. In one, a worker drops something heavy, but no one is hurt. In the other, the same thing happens, but someone is seriously injured. The mishap is the same, but the outcome is completely different. By analyzing the result, we can identify things that might have made the outcome more or less severe.
That makes sense. It's about looking at the whole picture and understanding the full impact of those mishaps, so we can make smarter decisions about how to prevent them.
Right. Maybe in that second scenario, the worker wasn't wearing steel-toed boots, which would have protected their feet. Or maybe the area wasn't blocked off, putting other people at risk. By analyzing the result, we can find those additional vulnerabilities.
Okay, so we've gone through all 7 parts of the modern causation model, and it's really impressive how it breaks down this complex problem into manageable pieces. But how do we actually use this model in real life? I mean, it's one thing to understand the theory, but how do we turn that into steps to prevent accidents?
That's a great question, and that's where those investigative tools and techniques we mentioned before come in. Things like root cause analysis, job safety analysis, and even more advanced methods like fault tree analysis or failure modes and effects analysis.
Okay, those sound pretty technical.
Yeah.
Can you give us an idea of how those tools work in practice? Like, let's say we're investigating an accident where a worker was hurt while operating a machine. How would we use those tools to figure out what happened?
Let's use root cause analysis as an example. It's all about asking why over and over again until you get to the bottom of the problem. So you might start by asking, why was the worker injured? Maybe the answer is because the machine malfunctioned. But then we ask, why did the machine malfunction? Maybe it wasn't properly maintained. So we go deeper. Why wasn't it maintained? Maybe the maintenance staff didn't have enough training or there weren't enough spare parts. We keep asking why until we find the root cause.
So it's like peeling back layers of an onion, trying to get to that core issue that started the whole chain of events.
Exactly. And once we know the root cause, we can come up with targeted solutions to prevent it from happening again. Maybe that means having a stricter maintenance schedule, providing more training, or even redesigning the machine to make it safer.
Okay, so root cause analysis helps us figure out what happened and why. What about those other techniques you mentioned, like fault tree analysis and failure modes and effects analysis? What do they add?
Those are more specialized techniques that are especially useful when you're analyzing complicated systems and processes. Fault tree analysis, for example, helps us visualize how different events work together to cause an accident.
So it's like creating a map of the accident, showing all the paths that led to that final outcome.
Exactly. Imagine a tree with the accident at the top and all the contributing factors branching down from it. We can see how those factors interact and which ones are most important in causing the accident.
And what about failure modes and effects analysis? How is that different from fault tree analysis?
FMEA focuses on potential failures within a system. So we might look at a machine and identify all the ways it could break down, what would happen if it did, and how likely those failures are to happen.
So it's like a proactive risk assessment, figuring out what could go wrong and then finding ways to prevent it.
Precisely. And by doing this analysis ahead of time, we can often build safeguards into the system. We can implement preventive maintenance or even have backup plans to minimize the impact if something does go wrong.
These techniques are amazing. It's like we have this whole toolbox to help us understand and prevent accidents. But I imagine using these tools effectively takes a lot of skill and experience.
You're right. Accident investigation is complicated, and it often needs special training and knowledge. But the good news is that anyone can use the basic principles of these techniques, even if you're not a professional investigator.
So even if we're not experts, we can still use these ideas to improve safety at work and in our lives.
Absolutely. The key is to develop a curious mind, to wonder why things happen, and to be willing to ask questions and dig deeper to find the root causes of problems.
This has been such an insightful conversation. I feel like I've learned so much about the science behind safety.
I'm glad to hear that. And remember, learning about safety never stops. There's always something new to discover, and we can all do our part to make the world safer for ourselves and everyone around us.
Welcome back to Key Safety Talks. I feel like my head is spinning with all these insights about accident causation. We've covered so much, those classic dominoes, the modern causation model, all those amazing tools for analysis and prevention.
Yeah, it's been quite a journey, and we've really only just touched on this huge field. But what's really cool is that understanding these things can actually help us prevent accidents.
Right. You said before that even if we're not safety experts, we can still use these ideas. I'd like to talk more about that. How can we develop that safety mindset?
It starts with being aware and curious. Look around you, at work, at home, even walking down the street. And start asking yourself some questions. What are the dangers here? What could go wrong? How can I keep myself and others safe?
So it's about training ourselves to see those potential problems, the things we might miss because we're so used to them.
Exactly. And the more you do it, the more natural it becomes. You'll start noticing things like loose handrails, messy workspaces, frayed electrical cords, even just slippery floors, things that might seem small but could cause an accident.
So once we've spotted those hazards, what do we do?
Take action. Sometimes it's simple, like cleaning up a spill, fixing a loose cable, or telling someone about a hazard. Other times it might need a bigger solution, like redesigning a workspace, creating a new safety procedure, or providing more training.
Okay, so awareness leads to action. But what about when you can't get rid of the hazard entirely? How do we manage those risks?
That's where risk assessment comes in. It's a process for identifying hazards, figuring out how risky they are, and then doing things to reduce those risks.
Can you take us through that process? What are the steps?
First, you have to identify the hazards. This means looking closely at the task, the equipment, the environment, anything that could contribute to an accident.
So it's like a detailed inspection looking for anything that could cause harm.
Exactly. Once you've found the hazards, you need to evaluate the risks. This means thinking about how likely the hazard is to cause harm and how serious that harm could be.
Right. So a hazard that's very likely to cause serious harm would be a bigger risk than one that's unlikely to cause much harm.
Exactly. And once you've assessed the risks, you can move on to the most important part, putting control measures in place.
Can you give us some examples of control measures? I imagine they can be very different depending on the situation.
Absolutely. Control measures can be simple precautions like wearing PPE, or more complex solutions like engineering controls or administrative controls.
Okay, can you give us some specific examples?
Sure. Let's say we found that workers on a construction site are exposed to loud noise. A simple control measure would be to give them hearing protection, like earplugs or earmuffs. A more complex solution might be using quieter equipment or putting up noise barriers to reduce the noise at the source.
So it's about finding the best way to minimize the risk, whether that's through personal protection, engineering solutions, or changing how work is done.
Exactly. And the hierarchy of controls gives us a framework for deciding which control measures are most important.
What's the hierarchy of controls?
It ranks control measures from most effective to least effective. The best controls are the ones that get rid of the hazard altogether.
Can you give us an example?
Imagine a factory that uses a dangerous chemical. The best way to control that hazard would be to stop using the chemical, maybe by switching to a safer alternative.
That makes sense. What if you can't get rid of the hazard completely?
The next best thing is substitution, which means replacing the hazard with something less dangerous. For example, if you can't stop using a certain solvent, you might try to find a solvent that's not as toxic or flammable.
Okay, so elimination and substitution are at the top. What comes next?
Next are engineering controls, which means making physical changes to the workplace to reduce the risk. For example, you might install ventilation systems to remove harmful fumes, or use machine guards to prevent workers from touching moving parts.
So engineering controls are about changing the environment to make it safer. What about administrative controls?
Those are about changing how work is done to reduce risk, like having safe work procedures, providing training, or rotating workers so they're not exposed for too long.
So administrative controls are more about changing behavior and processes than making physical changes to the workplace.
Exactly. And lastly, at the bottom of the hierarchy, we have personal protective equipment, or PPE.
Things like gloves, hard hats, safety glasses, and respirators.
It should only be used when other controls aren't possible or aren't enough to make things safe.
I see how this hierarchy of controls gives us a clear way to prioritize safety efforts. It's all about starting with the most effective controls and going down the list.
Exactly. And by using this hierarchy, we can create a multi-layered approach to safety, making sure we're doing everything we can to protect workers.
This has been an incredible look into accident causation and prevention. We've learned so much, from the basic theories to the practical tools and techniques used by safety professionals.
It's been great sharing these insights with you. And remember, safety is an ongoing journey. There's always more to learn, and we can all help create a safer world.
Thank you for joining us in Key Safety Talks. Stay curious, stay safe, and we'll see you next time.